When thinking about how computers work, one of the first things that people dig into is binary numbers. This video aims to take your knowledge of binary numbers and what they are and move it to the next level. But first, a review of what a binary number is. So here's a binary number. It's 8 bits. We either have the possibility of putting a 0 or 1 into each of these bits, and we read it from right to left. So we think of that first bit as representing the number 1 in base 10, the second bit representing the number 2, and then it goes up as a power of 2 as we go forward. In this case, this number equals in base 10 or decimal 13. And that's because we add the fourth bit that we read from the right, that 8, to the third bit that we read from the right, the 4, and then our first bit, which is 1. We could basically ignore any bits beyond the 8 to the left, but we may represent zeros as leading zeros in the binary number, basically to denote places in memory that we can use to represent the number. But if our number really stops its 1 bits at the 8 position, for example, we can just write it as 1101 if we want. So here are a bunch of binary numbers. So pause your video for a second and go through all three of these numbers, the one on the top row, the middle row, and that bottom row, and figure out what the number is in base 10. Your process for doing this will be to figure out where the ones are and what base 10 number represents that position, and then add those numbers together. So go ahead, pause your video, and take a second to do that. So hopefully you paused there and figured out some of your own answers, but let's compare. So this first number at the top, 00010110. In binary, this is the number 22. So how do we get there? We take the 1 in the 16 slot, which means that we're going to add 16. We take the 1 in the 4 slot, so 16 plus 4, that's 20. And then the 1 in the 2 slot, which is 20 plus 2, which is 22. And that is the number that we have here for that binary number. That's our decimal number. That's our base 10 number, kind of converted from this base 2 or binary number. The second one, we say 64 plus 8, and that is 72. And then we add 4 to 72, giving us 76. And then we add the 1 position. And then that means that this second number is 77. And then this last number, where it's all ones for all 8 of these bits, this is an important number. We see this number a lot. If you ever think of RGB values like red, green, blue, what you can pick when you pick one of those colors is you can pick a number between 0 and 255. What RGB is doing is it's representing your red, green, and blue channels as a value between 0 and 255 as an 8-bit number. So all ones is 255. We add 128s to 64 to 32 to 16 to 8 to 4 to 2 to 1, and we get 255. And we don't have to stop at 8 bits. We can keep going beyond the 8 bits. We can go past that 128 that we saw in those 3 numbers before and continue to build our binary number, and we just let it go up by 2 to the next power. So beyond 128, we see 256, which would be 1 more than our 255 if we had all the ones in those first 8 bits, right? So we could make all of those first 8 bits 0 and then put a 1 in the 256 place, and now we have the number 256. And this just like continues on. This just gets bigger and bigger as we go to each slot in the binary number. So let's say we were building an application for like a resort, maybe in Hawaii or something like that. You know, something nice. One of the things that we do at this resort is we give a perk to all of our guests. So every guest at one time, free of charge, can do each of the following activities. They are eligible for 1 hour in the private sauna, a kayaking excursion with one of our professional teachers, a free dinner with room service, a free sunrise yoga lesson. And what we want to do is we want to find a way to keep track for a guest. And here's a guest that we have staying with us, guest Bobby. His name is Bobby. He's staying in room 105, and he's checking out on July 25th, 2021. We want to keep track of which of these perks has Bobby used so far. He's eligible for all 4. So which of them has he used? So I would say pause the video, take a second to think about how on this object, on this structure, guest Bobby I have in the corner, you would represent how to keep track of the 4 perks that Bobby is eligible for and whether or not he has, in fact, claimed any of those perks. Welcome back. There's lots of ways to go ahead and represent this for sure. Here's one way. Here's one way that we could have kind of came up with. Maybe the guest structure, how we represent one of the guests in our resort application, has a property called claimed perks, which is an object that would have for our 4 possible claimable perks a Boolean that represents whether or not they have claimed that perk. So in this case, Bobby has yes claimed the sauna perk, has not claimed the kayak perk, has claimed the dinner perk, and has taken his sunrise yoga lesson. And this is, you might have done this in a different way, and that would be totally fine. But what if I told you that you could represent which perks Bobby has used with a binary number? So what we can do is we can establish that each perk, the sauna, the kayak, the dinner, and the yoga lesson, is represented by a different slot of a 4-bit binary number. And in Bobby's case, Bobby has indeed gone to the sauna, has not taken the kayaking excursion, has had free dinner with room service, and has gone to his yoga lesson. So we can say 1 in the sauna slot, 0 in the kayak slot, 1 in the dinner slot, and 1 in the yoga slot, thus giving us the base 10 number from this binary number, 11. 8, which is that 4th bit, 2, which is that 2nd bit, and 1, which is that 1st bit. And so instead of an object with all those booleans and the property names that we had before, we could just put the number 11 here, which means that he's gone to the sauna and the dinner and the lesson, but not the kayak. We might even write it as a binary number directly in our object, by the way. JavaScript has notation for you to write a binary number. So you can see here on next to claimed perks, it is 0B1011. But when we look at the property, it will be a base 10 number. So we can see that 11 is here instead. So let's look at some other guests. We know that Bobby has gone to the sauna, has not done kayaking, did go get his dinner, and did go to the lesson. Therefore, we have that binary number in the top left and the base number 11. So what about some other guests? We have Jesse, Mary, and Joe. You can see the excursions or the perks that they've used so far with the check marks and the X marks as well. So pause the video and figure out, based on what they've done, what binary number can be used to represent which perks they've taken, and then what is the base number based on that binary number. After you fill in the zeros and ones, figure out what the decimal number would be for that binary number. So let's look at my answers. We have Jesse, who has not gone to the sauna, has gone kayaking, and hasn't done any other perks beyond that too. So his claimed perks binary number is 0100, or the base number 4, because we have the 1 in the 4 slot. Mary has done everything but dinner, so her number is 1101 or 13. And then Joe, he gets everything out as soon as possible. Yeah, every perk is his domain. So he quickly used his perks. So he went to the sauna, went kayaking, had dinner, and went to his yoga lesson. Therefore, he has 4 ones or the number 15 in base 10. So what we're working with here can be called a data structure. If we have a set amount of bits, like these 4 bits that represent the 4 perks that we provide at the resort, we can use the bits to say whether or not any specific guest has claimed the perk or not, and use the binary number as a result as a sort of like allocated value for whether or not each perk has been taken. So if we have a bit field like this one that represents which perks Bobby has claimed, how can we use this value and check things about it? Like, for example, has Bobby claimed the yoga perk? Obviously, when we're looking at it, we can intuitively see that. We see the yoga emoji. We know that it's that first spot, and there's a 1 there. So how can we actually like make this happen in our own code to take a binary number like 1011 or the number 11 and know that, yes, Bobby has claimed the yoga perk? Well, Useful here is going to be our first bitwise operator known as the AND operator. So you may have seen this in JavaScript before, but maybe not. But this is a way, this operator lets you take two binary numbers and compare them and say, do both of these numbers have 1 in the same slot? We have the binary number 11101000, which is the binary number for 232 because we take 128 plus 164 plus 32 plus 8, and we get 132. And we AND that. We use this operator AND to compare it to another binary number, in this case the binary number 10100001, or in base 10 161. It will check both of these numbers and see if they both have a 1 in that position. So if we look through the check marks and the crosses here, we see in that 128 position, that 8th bit, we have a check mark because both of these numbers has the 128 there. Another way to look at this is if you look at the green numbers all the way on the right, and we see the ones that are being added up in base 10. Essentially what an AND does is as long as the slot is being used by both numbers, it will end up in the resulting number, which is what we see here on the bottom. Because the first and second binary number both have a 1 in the 28 slot, the 128 slot, and then also both have a 1 in the 32nd slot, that 6th bit, then we have a resulting number of 160 because we add 128 and 32. So how do we use the bitwise AND operator then to figure out if Bobby has done yoga? Well, we have Bobby's claimed perks as the 1011 or base 1011. And then we have what is known as a bit mask. So this bit mask, which you can see in the top right corner, the has done yoga bit mask, this is a number that basically has all of the things that we want to know is also 1 in a number that we're comparing it to. So you can see that sauna 0, kayak 0, dinner 0, and then yoga 1. And what we can do is we can use the AND operator to compare these two numbers. We can say, let's take Bobby's claimed perks and let's AND it against the yoga bit mask. And as long as it spits out a number that's greater than 0, which in this case it spits out the number 1 in binary, then we know that yes, Bobby has done yoga. So let's say that Bobby didn't do yoga. Let's say that Bobby's claimed perks was 1010, which would be the base number 10. We would have 1010 ANDed with our yoga bit mask, and because none of these slots have 1 in both numbers, we end up with the spit out number 000, which we can think of as just 0, which is 0 in binary and in decimal and everything else. So we just check to see if this output value is 0, and if it is 0, then Bobby has not done yoga. If it's 1, then Bobby has. And we would essentially just use different bit masks in order to figure out yoga versus dinner versus kayaking versus sauna. So let's pause our video again and figure out what the bit masks would look like for each of these different perks. All right, let's compare answers. So what I got was for the dinner bit mask, which you can see in the top right, we have 001 where the dinner slot is, and then 0 for yoga, and then that's the base number 2. And then we have 0100 for the kayaking bit mask, which is number 4, and then 1, and then trailing zeros for the sauna bit mask, which gives us the base number 8. Let's actually write some code that kind of explores these ideas. So this will be some JavaScript code. And what we're going to do is we're going to set up a code base that we can have one of these guests as an object like we've been discussing, and then a couple bit masks that we can use to compare whether or not their claimed perks include yoga or include sauna and stuff like that. So the first thing that I want to do is I want to set up our different bit masks. I want to say const has done yoga like this, and say that this is going to be equal to, and we can write this a couple of different ways, but let's think about our bit mask. This is going to be 0001. So we can write this as 0b0001. This is a notation that is valid in JavaScript. We can do it this way. We could also just write the number 1 because that is what 0001 is in base 10. So we can do it either way. So we can write it in both of these ways. And I'll be kind of like switching my strategy for this just to show what's possible. So has done dinner. That is our second slot. So this would be the base number 2, but let's write it as the binary this time. Let's say 0B 0 0 1 0 like that. This would be base number 2. And we're just setting up these bit masks. We're setting up these numbers so that they can be used with the bitwise AND operator later when we have a claimed perk. So let's do our last two. We have has done kayak, and this is going to be 0B 0 1 0 0, or the number 4. And then has done sauna, and this is going to be 0B 1 0 0 0, or 8. So next up, let's console log these. Let's see what these actually look like. If we were to console log each of these, one after the other, has done yoga, copy that down, and then replace it with dinner, kayak, sauna, and just run this real quick. You can see right below me, we have the logging out of 1, 2, 4, and 8. Even though we're defining it with binary numbers, they always kind of get inspected as base 10. That's something to realize about how the numbers work in JavaScript is they're all natural numbers, but when you inspect them, when you log them out, you're always going to see them in decimal form, even if you've originally notated them as binary or hexadecimal or octal or something like that. So now let's set up our guest Bobby. We're going to be using guest Bobby here to make this comparison. So here's guest Bobby. We're going to set up an object. There can be many properties on this object, but I'm just going to put name and then focus on what we're exploring, which is his claimed perks. So claimed perks, as we discussed, we can define it as a binary number, or we can define it as a decimal number. So I'm going to say 11, which is the binary number 0B for 1011, right? So 8 plus 2 plus 1. So Bobby has done everything except kayaking, because we use that third bit here to define the kayaking slot. Okay, so what we can do then is maybe set up a function that's going to print out, if you were to pass a guest in, which perks they have used. So let's create a function called print claimed perks. This is going to take a full guest object with the name property and the claimed perks property. And then we are going to use the bitwise and our bit masks in order to compare. So we're going to say, here is the claimed perks off of the objects and their name. Just use a little bit of destructuring there. And then we'll say if claimed perks and then bitwise and. So remember, this is going to then compare 1011, which is Bobby's claimed perks, to, and then let's do yoga first. Has done yoga. So this will be a bitwise and of 1011 and 0001. And remember that bitwise and basically just compares the numbers in each position of each bit to see if they both have 1 in that position. And then it will spit out a number that matches that position. And with the mask, we only have 1 in one position. So as long as the first operand, the left operand, the claimed perks in this case, has 1 in that same position, then we'll see basically the bit mask be its result. And then if that's greater than 0, if we can also say if it's not 0, because we shouldn't expect this to be a negative number either. As long as this is not 0, then we know that this perk has been claimed. Now be careful. Be careful, because what you want to make sure that you don't do is order of operations. Let's wrap this operation here, where we have the bitwise and, in parentheses, so that we can get the result of that and then compare it to another number like not equal to 0. And then here we can say console log, and then let's use a template literal, and we'll say name has done yoga. Cool. And we can do this for all of the other possible perks as well. We can say, let's copy this down, has done dinner, has done dinner, kayak, kayak, and finally sauna. sauna. Cool. So now we have this function print claim perks. We have a guest to test it with. So let's see. Let's do print claim perks guest Bobby. Run that and see what it outputs. So you can see here in the output, it says Bobby has done yoga, Bobby has done dinner, Bobby has done sauna, but we do not see anything for Bobby has done kayak. And that's because that third bit where we have the mask being checked for kayak is not, it ends up being 0 because the mask never sees a double 1 when it's doing its bitwise and. So quickly testing with some more input data, we have Bobby like we did before, and we're going to set his claimed perks to be 11 like this, so, or 11. We have Jesse, who has only done the kayaking, so his claimed perks is 4, or binary 0100. We have Mary, who has done everything except dinner. And then we have Joe, who has done everything. Therefore, his binary number is 1111, just like we saw earlier. So now if I were to print claim perks for each of these, we should see some matching results in which we see that Bobby has done everything except kayaking. Jesse has only done kayaking. Mary has done everything except dinner. And then Joe has done everything, every perk. So knowing this trick with bit fields and using the bitwise operators like the bitwise and to find state off of a bit field, you might get a sense of like a little bit of the insight of how a computer works at its base level, right? You can think about computers as being like a vast city of lights, 0 and 1, and the computer relates those lights together in order to come up with ideas and represent ideas and structures and related data. With the bit field, we can kind of like see that in action. Even if it's just 4 bits, we can represent a lot of state just inside. And there's a lot of places to go next, but what I want to show you next is something called bit shifting. So like the bitwise and operator, there are some more operators meant specifically for bit sequences or binary numbers built into JavaScript, which you may have seen before, but here's what they are. We're going to focus on the left shift for now. So the left shift operator shifts the operand that you combine with it, so a binary number, a specified number of bits to the left. Any bits that go beyond the left side, larger than how JavaScript can represent a large number, will be discarded, and any 0 bits that come in are shifted in from the right. I think that this is a lot easier to see with examples. So let's say that we have the binary number 0001, which we have right here. If we were to use the left shift operator, so the double less than symbol, and then the number 1, which we could also use binary number here, of course, then what we would have as a result is the number 0010, shifting that 1 at the beginning to the left, really shifting every bit to the left, and then putting a 0 at the beginning. And then if we did the same number, 0001, with left shift 2, we would see that 1 from the beginning go over twice. So bit shifting 1 by 1 to the left would give us 2, or the binary number 2, 0010, and then bit left shifting it by 2 would give us the number 4, or the binary number 0100. And then if we had a binary number like this one on the bottom, 1101, thus being the number, let's see, 13, 8 plus 4 plus 1. If we were to shift that over 4, what we would end up with is an 8-bit binary number, 11010000. So you see those 4 zeros at the beginning of the number go in, and then everything gets shifted. So this would be then 128 plus 64 plus 16, whatever that number is. So one thing that we can do with this bit shifting idea, for example, is to set up our bit masks a little bit more systematically. So here are the bit masks for our 4 claimed perks that we used in the previous example. And here are those related bit masks here in our code sample, here on lines 3, 4, 5, and 6. So using bit shifting, this idea of left shifting the binary number, how could we more systematically set up these bit masks other than hard coding the binary numbers or the base 10 numbers in here? Pause the video, think about how you would do that, maybe write it out for yourself, and I'll be back in a second. Okay, so let's do a little bit of refactoring. Before I go any further, I want to make sure that I'm just looking at these values and that after I make that little refactoring with bit shifting that they end up looking the same. So let's go ahead and just log them out one at a time. And we should see 1, 2, 4, 8 here. And we checked this out earlier. But we should see the same thing. So let's run this. You can see the output below me, and we have 1, 2, 4, 8. Perfect. So back to it, what we're going to do is I'm going to comment out how we've been assigning these bit masks here and rewrite them. So has done yoga. What this is going to be is it's going to be the binary number 1. And then what I'm going to do is I'm going to shift it to the left 0 times, which basically means that this is like a no op. It doesn't really do anything. It just kind of spits out the same binary number. So then this would be 0001 or just 1, and then in decimal also 1. And that is what our has done yoga bit mask is supposed to be. So let's do the dinner one. So this one is supposed to be the binary number 0010 or just 10. So what we can do is we can take that 0001 and left shift it 1 time. This is going to give us a resulting binary number of 0010, which is in decimal 2. And that is exactly what we had before. Then we can do this 2 more times. We can say for kayak, well, let's shift that twice, right? Which would result in 0100. And then let's shift finally sauna 3 times to move that 1 bit to the 4th position instead of being in the 1st position, thus being 1000 or the base number 8. So just updating these comments here. That's what we kind of end up with. And then let's run this and see if we get the same output. And you can see we still get 1, 2, 4, 8. So this is a cool way to kind of set up our bit masks automatically. If this kind of seems like it's like array indexes where like you have index 0, index 1, index 2, index 3, you might have something there. You might be seeing kind of like under the surface of how computers think about things by recognizing that pattern. So something I haven't told you about our 4 guests at the resort is actually they're all part of the same family. Bobby, Jesse, Mary, and Joe, they all came as a unit to enjoy the resort life, and they each get their free perks. So what if we wanted to find a way to know in the whole entire family what claimed perks have been taken? We know how to represent it per individual, but what if we wanted to come up with a bit field or binary number that represents all of the claimed perks across the whole family? Well, what we could do is we could take the 4-bit binary numbers of each individual and combine them. What we can say is the binary number that represents the total claimed bits of the whole family is a combination of Bobby's 4 bits being at the very beginning of the number or the leftmost in that number, and then Jesse's 4 bits, you can see 0100, and then Mary's 4 bits 1101, and then finally Joe's 4 bits 1111. And we combine all 4 of them into a larger binary number, which represents first of all of the possibilities of all the claimed perk configurations from the whole family, and then also the current state of all claimed perks for the family. Let's explore this logically in code. So here we have our family unit in an array right here with each family member as an object. We have Bobby, Jesse, Mary, and Joe with all of the claimed perks values that we've been seeing in the slides. So if we wanted to come up with a larger binary number that represents all of their perks put together, we need to combine each of these other numbers. This number 11 or 1011, etc. So I think that there's lots of ways that you might go about do this. I think that array.reduce is a great thing to use here. It's kind of like exactly what reduce is for. So we're going to say total family claimed perks. And this is going to be the result of us reducing the family array. So we're going to say family array reduce, provide our accumulation function here, and then our initial value. And this initial value is going to be 0. We could also say binary 0 like this, but we're basically going to say that we have like an empty set. And then we have each family member coming in. Well, first of all, we have our accumulator. So this is going to be our total perks value, which is going to start at 0. And then we have each family member here. So we're very interested in the family members claimed perks. So let's just put that on a variable if we want. So family member claimed perks. We can also use destructuring. And now what we're going to do, here's where we're going to get kind of magical. So the binary number that we have to start off with is 0. And if we were to bit shift to the left 0 4 times, we would also have 0, but we can kind of imagine that we have like 4 empty spaces. So if we say like with some room, this might be an okay variable name for this. We're going to say, let's take the total perks value that exists now and shift it to the left 4. So if we have, 0, it's actually kind of hard to think about it at first, but once we get some data in there, it'll be easier. We're going to basically turn 0 into 4 empty spaces. And then what we're going to use is a different bitwise operator than the AND. We're going to use OR. So similar to bitwise AND, but thinks differently, bitwise OR is built into JavaScript, and it returns a 1 in the resulting number for each bit position that either has, it just has 1 on either side, right? With AND, we were checking to see if, like, for example, the 128th place of both of those binary numbers both had 1, but the OR just checks to see if one of them has 1. So going through an example, let's say that we have the same numbers we were looking at earlier when we were talking about AND. We have 232, which is its top number, and we have 161, which is the second number, and we use an OR. The way that this would compare is in the 128 position, for example, we have 1 and 1 that would go through. But then what's different from what we had before, in the 64 position, you can see the first number, 232, does have a 1 in the 64 position, but the second number doesn't. It has a 0 there, right? This would still go through. This would end up being a 1 in the resulting number right here, because the way that OR thinks is it doesn't have to have 1 in both, it just has to have 1 in 1. So we have the resulting number, which basically just carries over all of the positions from both numbers, because every used position is kind of maintained in the resulting number. So as we bit shift our total perks value over to the left 4, we end up with some zeros as an empty space at the beginning of the number, which then we can use a bitwise OR to fill in. We can take the claimed perks of every individual and just replace those first 4 empty bits with whatever bits are being used for their claimed perks. If they're completely empty, then we just have an OR that spits out zeros. But every time a 1 takes place, we have that. So let's say that our total perks value through our accumulation already included Bobby's, right? So it would kind of look like this. We have Bobby's perks, which are 1011, right? Everything except kayaking, and then we bit shift that to the left 4, so we would end up with this number here with the 4 zeros at the end. And then if we were to do an OR operation with who's next, we have Jesse's, we would have this number. We can always imagine the leading zeros if we only have a 4-bit number. We can always think about that as many as JavaScript uses to actually represent the number, basically. And then Jesse's actual perks, which was 0, 1, 0, 0, like that. So if we were to do an OR here, right, what we would get is, let's compare. Let's say this slot has a 1, yes. This one does not. This does. This does. This does not, this does, this does not, this does not. So we basically then just end up with a binary number, which the first 4 bits are Bobby's bits, and then the next 4 bits are Jesse's bits. And then we can repeat this again, shift it over 4 to the left again, and then fill in Mary's bits, and then fill in Joe's bits. And then when we're done, we have one longer number. So we're going to say returning from this accumulation will be with some room, which is whatever value we have now, with 4 bits that are empty at the beginning, and then an OR with our claimed perks bits. And then if we were to console log that out and execute this, what we should have is a pretty big number. Let's see. Let's run this and see. So what we get is the number 46,303 in base 10. If you want to see what this looks like in binary, the trick is that you do toString on the number, and then you use the number 2, which stands for base 2, which says, I want to turn this number into a string of a base 2 number. And in that way, you can actually inspect how this looks when it's actually turned into binary from decimal. So we have this as the decimal number, and then this long binary number as the combination of Bobby's, then Jesse's, then Mary's, then Joe's bits. So you can kind of see that the beginning bits are 1011, which is Bobby's bits, and then the ending bits are 1111, which is Joe's bits. So we have Bobby's bits, right? 1011, and then we shift it over 4, which gives us this number here, 1011, 0000, and then we do an OR operation with Jesse's bits, which is just 0100, and then we have the 4 leading zeros because we can always put leading zeros on a limited bit binary number. And then that OR process basically just combines the two, right? We end up just kind of like appending Jesse's bits through using the OR, the bitwise OR operand in this way. And then if we have this really long number that's all of the family's perks as a bunch of bits, we can use the right shift operator to, first of all, inspect the first 4 bits. We can use an AND in order to do that. And then we can shift it off. So imagine that we had the long stateful number. We can look at the first 4 bits with an AND operator. And then we can say, okay, now that we have looked at Joe's bits, which is the 1111 at the beginning of the number, we can shift to the right 4. What's going to happen is that the 4 bits at the front are going to fall off the number and then basically be deleted. And then any bits that are now empty that get shifted forward, we can imagine as being empty bits or 0 bits. So we kind of can go through this number step by step until eventually the number's empty, right? We keep shifting over 4, getting a new number off of that. Eventually we'll go through all of our filled in bits and then just have empty bits that were put in by the shift. So examining this idea of taking information off of the long binary number in code, so if we wanted to go ahead and see, for example, the first 4 bits, which we can call Joe's bits, we can say, here's Joe's bits. It is going to be the total family claimed perks, and then we're going to use an AND, bitwise AND operation with the number 8. With the number 15, which we can also think of as binary 1111, which basically says that we don't want anything except the first 4 bits, right? Because that's what the AND does. It checks to see if both numbers have 1 in the right position. So it'll just go ahead and basically take the first 4 bits from the number off, and we'll get that back. So we can go ahead and take a look at Joe's bits. And we should expect this to be 1111 because we know that the total family perks binary number ends with that 1111. So let's go ahead and console log that out, and we should see 15 because that is the binary number 1111. And then if we wanted to update the total family claimed perks, let's go ahead and make that a let so that we can reassign it. So let's do total family claimed perks is equal to itself bit shifted 4 to the right, not the left this time, but 4 to the right. And then let's take a look at that. We'll just repeat this logging that we have here. And obviously, like the best way to probably do this is like in a loop or something. But this is good for our exploration. So we run that, and then you can see that that number got significantly lower in base 10, first of all. And then also is the same number, you can see here, if you compare it to the top, it's basically the same number without the first 4 bits. So we're just basically taking information off of this number as we go. So let's do it again. We're going to say that, who's next? Mary's bits. Mary's bits, since they were the second to last shifted on, we can say that that is total family perks and then the same process as before. Let's AND it with a 1111 so that everything before it is taken off, but then we get the we preserve Mary's bits at the very beginning, the first 4 bits. So let's take a look at Mary's bits, and let's take a look at it in binary as well with that toString 2. Go ahead and run this. So you can see Mary's bits in base 10 is 13, and then the actual binary is 1101 right there. And that is what we understand Mary's bits to be if we look up here. So she has done sauna, kayak, not dinner, and yoga she has done. And we can keep going with this. We can just keep like, you know, ANDing the first 4 bits, and then when we're done, shifting them over, which will give us the next slot that we can AND the first 4 bits against to re-access all of this state, which is like freaking awesome. A couple of things you have to be careful of is if at any point, let's say like the last state or bit field that you have in the combined bit field is 0000, you're going to have to make sure that you don't understand that as being an empty binary number or a 0 binary number, but actually being the state of somebody's bit fields if they haven't claimed any perks. So that's something you have to kind of keep in mind. In that way, you kind of have to like know how many times you need to check. You need to know the length of your binary number or the amount of bits you expect state to be sort of conveyed as in that number. But that's pretty easy. Just having like a length or expectation of length will help you there. So you're not going to solve every problem with this bitwise stuff. But binary numbers are really powerful. And when you do have a problem in which you have to solve it in an extremely memory efficient way or with very quick operations, keep in mind that computers are already thinking this way. They're already thinking in these sets of binary numbers. They use a lot of the techniques that we talked about in this video. So hopefully the next time that you encounter a problem that you can solve in this way, you'll think back to this video, come and revisit this video, and think about how you might set up a bit field and use bit shifting and bitwise operators to do some stateful operations and stateful storage of data in a binary sort of way. And of course, thank you for watching. This is actually my first YouTube educational video that I've ever made. I definitely learned a lot in the process of making it. But if there's anything else that you would like to learn or any comments that you have and you want to tell me that you like this video, didn't like this video, you know, do the YouTube thing, leave a comment. If you want to know when I've released a new video, go ahead and subscribe. And yeah, tell me what you want to learn because I'm thinking about what my next video would be about already. So if there's something that you are looking to dig into and you want some insight on, let me know and maybe I'll prepare that for you. So yeah, thank you everybody. Class is dismissed. See you later. Oh, it's a penny break. It's a penny break. Look, sweetie, say hi to YouTube. Hello, YouTube.